This is your presenter Asloop Mudassar, and I am presenting slide number 97 of the course on laser physics. Question is, how will you compute the pump efficiency in a general way relating it with the pump rate? The answer is, the efficiency of a laser pumping system eta P can be computed by computing four relevant efficiencies. Eta R, the radiative efficiency, eta T, the transfer efficiency, eta A, absorption efficiency, eta PQ, power quantum efficiency as given by. So eta P, which is the laser pumping efficiency, eta P is equal to the product of four efficiencies, eta R, eta T, eta A, and eta PQ. These efficiencies are defined as given. Eta R, which is the radiative efficiency. It is by definition, it is given by optical power falling in the absorption band of laser medium divided by the electrical power input to the pump system. Eta T, which is the transfer efficiency, defined as optical power incident on the laser medium divided by the optical power falling in the absorption band of the laser medium. Then eta A, absorption efficiency, is defined as optical power absorbed by the laser medium divided by the optical power incident on the laser medium. And then eta PQ, which is the power quantum efficiency, is defined as optical power converted to populate upper laser level divided by the optical power absorbed by the laser medium. And then it is given by, in terms of mathematical quantities, is equal to Rp multiplied by V, capital V, multiplied by H nu divided by Pa. We come back to this formula, but first let's concentrate on the efficiencies that we have just defined. You see that I have given the colors, different colors to the numerator and denominator. For example, in the numerator of the NR, the color is red. And in the denominator for eta T, the color is red. So when we multiply the efficiencies, the numerator in the NR, the numerator in the eta R is cancelled by the denominator in the eta T. So look at the numerator in the eta T shown in the blue light. And then of course the eta A, the denominator of the eta A is also shown in blue. So it means that the numerator in the eta T will be cancelled by the denominator in the definition of eta A. Because and as you see that I have shown, that's why with the same colors. And then you can see that the color in the numerator of the eta A is shown in green. That is the optical power absorbed by the laser medium. And then you see that in the definition of the eta PQ, look at the denominator, which is the same quantity shown in green, optical power absorbed by the laser medium. So when eta A and eta PQ will multiply to each other, then of course the numerator in the eta A expression will be cancelled by the denominator in the eta PQ expression. Then what shall we survive? You see that all the quantities will be cancelled except this quantity is left at the end, which is shown in bold. That is the optical power converted to populate upper laser level. So this will survive, you know. So this will form the numerator in the final expression. And another quantity that will survive is shown as in the denominator of the eta R, which is electrical power input to the pump system. So this will survive as the denominator in the final expression. So we have the final expression that is the efficiency eta P. Then in the definition of eta P, the final expression that will survive will be equal to the optical power converted to populate the upper laser level divided by the electrical power input to the pump system. So if we represent the electric power input to the pump system by PE and represent the optical power converted to populate the upper laser level by PM, then you see that eta PQ will be equal to PM over PE, where M is the subscript with P and E is the subscript with E. So eta PQ will then be equal to PM over PE. Okay, so you see that according to the numerator, according to that the numerator in the expression of the eta P will survive. That is the and the mathematical term which we have shown in equation number 5. The numerator in equation number 5 will also survive. That is RP multiplied by capital V multiplied by H nu will survive. So let's analyze these terms. Where PA, the denominator of equation number 5, that is the optical power absorbed in the active medium. Nu is the frequency difference between the upper and the ground laser levels. Rp is the pump rate defined as dN2 over dt, and with the subscript P stands for the pump rate. So it will increase the population of the level 2 with the time. And you know that it is the number of particles per unit volume raised to the upper laser level by the pumping process. Since this is the number per unit volume, you will multiply it with the volume, so that it will give you just the number. So when you multiply Rp with capital V, which is the volume, then you will get the number of particles that are used to raise the upper laser level by the pumping process. So capital V here is the volume of the active medium. LAMP's spectral emission and LAMP's geometry along with the active medium's absorption coefficient and medium's geometry are the useful parameters to determine an explicit expression for eta P. So you see that eta P depends upon many of these parameters that I have just mentioned. We are not going to discuss in detail the dependence of eta P on these parameters, but we are just going to derive a mathematical expression for eta P, which is the efficiency of the pumping process. So for pulsed lasers, pulsed pumping. For pulsed laser, we require pulsed pumping. The term power will be replaced by the term energy when we are talking about the pulsed formation. So for the pulsed lasers and for the pulsed pumping, we shall be using the term energy rather than the power. So now let's give a general formula applicable for both the continuous wave laser and for the pulsed lasers, or for the continuous pumping or for the pulsed pumping. The pump efficiency eta P can be simply defined as eta P is equal to PM over PE, where PM is the same thing as we have defined earlier. So PM is actually equal to the optical power falling in the absorption band of the laser medium, not this one. But what then it is, because this will be cancelled out by the denominator in eta T. So it means that this PM is actually optical power converted to populate upper laser level. And the mathematical expression for that one is capital RP, capital V multiplied by H nu. So this is this numerator in equation number 5 is actually PM. And what is PE? PE is the electrical power given to the input pumping system. This one in the denominator of equation number 2. So we have PM over PE. The expression of the PM is given earlier, you see, mathematically. But let's discuss it in detail. Where PE is the electric power input to the pump, and PM is the minimum optical pump power required to produce a given pump rate RP. So PM by definition is given by PM is equal to H nu multiplied by the integral of RP multiplied by dV element. And you know that the total volume element will be the element of the active medium. So you see that this integral can be solved under two conditions. Either we shall assume that since we are talking about in the for continuous laser, that is for continuous pumping, so we can here assume that is the RP is the average pump rate. So if we assume that RP represents the average pump rate of the pumping process, then we can represent it RP by RP prime. So we can take it outside the integral, and the integral of dV will be equal to capital V. So then the final expression, assuming that assuming that RP is the average pump rate, which is constant, we can take it outside the integral, and the PM will be equal to H nu multiplied by RP prime multiplied by capital V, as shown on the right hand side in equation number 7. The integral covers the whole volume of the active medium, and RP prime is the average pump rate. So this was the one option that we used, the average pump rate, average pump rate assumption, and then we represented RP by RP prime and took outside the integral. The second option is that we don't use the average value, and we just say that the pumping is uniform. For uniform pumping, RP can be moved outside the integral, then we can write. So you see that if the pumping is uniform, we can simply take RP outside, and then we have this integral solved on the right hand side in equation number 8. That is PM will be equal to H nu multiplied by RP multiplied by V. So you see that this equation 8 is the same as the equation given over here in the numerator of equation number 5, the same expression, RP multiplied by capital V multiplied by H nu. And you see that this you must understand that the numerator in equation number 5 was written assuming that RP is a uniform variable, that is, it's not going to change. So it is the uniform pumping rate. Now you see that thus for a uniform pumping rate we can obtain eta P, and you know that eta P by definition, as we have defined it in the definition given in equation number 6, that eta P is equal to PM over PE. So using the value of a PM that we have derived in equation number 8, we can write equation number 9 as eta P is equal to H nu multiplied by RP multiplied by capital V divided by PE, the electrical power given to the pumping system. And we can solve this equation for the value of RP in terms of the other quantities. So you see that this expression given in equation number 10 is only useful when eta P is known. So if eta P is known, then RP can be computed. Now you see that for a pulsed laser system, as said earlier, that we shall not using the term power, but we shall using the term energy. So PM in the definition, that is in the definition that we have given over here, that is the PM will be converted to EM, that is energy. We shall not talking about the power when we are talking about the pulsed systems, that is the pulsed lasers or the pulsed pumping. So we are now going to replace PM by EM, and the integral will be equal to H nu double integral over RP and dV and dt. So we need to solve this integral if we know the value of these, because we now have to calculate the total energy, not the power, and then of course the electrical energy will also electric power will also be converted into the electrical energy, which is given by EE. So for the pulsed systems we shall be talking about EM and EE, and this integral can only be solved when the when the relevant information is provided. For the time being, we are just leaving these things over here, just to saying that the power will be converted into energies when we want to calculate these efficiencies for a pulsed system or for a pulsed pumping system. So this is the end of slide number 97.